Researchers from Georgia Tech and Tianjin University have made a groundbreaking discovery in the field of semiconductor materials. Their new technology has the potential to revolutionize the world of electronics by creating computer chips that are significantly faster than ever before. In this video, I will explain why. So let's dive into the video. Moore's law, proposed by Gordon Moore in 1965, states that the number of transistors in a chip doubles approximately every 2 years. However, as technology has advanced, it has become increasingly difficult and costly to fit more and more transistors into a single silicon chip. Currently, we are able to fit around 200 million transistors per square millimeter, a remarkable achievement. However, further scaling down the transistor technology presents a significant challenge. The size of a single atom is one of the physical limits we are starting to encounter. To overcome these limitations, researchers have turned to a new approach, stacking transistors on top of each other in the third dimension. This allows us to fit more transistors in the same area, similar to a densely populated city growing vertically. However, this approach also introduces a new problem. Vertically stacked devices suffer from a heat dissipation issue, as there is no heat dissipation path. Overheating can degrade the performance and lifespan of electronic devices and even lead to a meltdown. Exploring new semiconductor materials. To address the heat dissipation problem, researchers have been searching for new semiconductor materials that can offer better heat dissipation than silicon. Graphene, with its exceptional thermal conductivity, has been a promising candidate for a long time. Graphene is a unique material due to its particular crystal structure. It has much higher thermal conductivity than silicon, making it an excellent option for thermal management in electronic devices. However, graphene has one fundamental drawback. It is not a semiconductor. It has a zero band gap, meaning it is highly conductive like a metal. Despite the challenge posed by graphene's lack of a band gap, researchers have found a way to make a perfect semiconductor out of graphene. By growing graphene on top of a silicon carbide wafer and introducing impurities, they have managed to create a new semiconductor material called semiconducting epigraphene, or SEG. SEG offers the best of both worlds. It retains the desirable properties of graphene, such as thermal conductivity, while also having a band gap that allows for switching between on and off states. This breakthrough opens up new possibilities for creating faster chips with less heat dissipation. Epigraphene transistors, built on a silicon carbide substrate, have shown great promise. When a gate-to-source voltage exceeds a certain threshold, the transistor is turned on, allowing current to flow through the channel. These transistors have the ability to switch quickly and support frequencies in the terahertz range. The high electron mobility of graphene enables these transistors to achieve 10 times higher electron mobility than traditional silicon chips. Electron mobility is defined by the crystal structure of the material, and graphene's flatness and band structure allow electrons to move faster through the semiconductor. This translates to faster chips with reduced heat dissipation. Boron Arsenide is another potential candidate to replace silicon due to its impressive properties. It offers improved charge mobility and significantly higher thermal conductivity than silicon. However, fabricating boron arsenide in high volumes defect-free remains a challenge. While it may take time and significant investment, the potential for boron arsenide and other alternative semiconductor materials is immense, just as it took several decades for silicon to become the dominant material. We can expect a similar journey for these new materials. The development of semiconducting epigraphene and other alternative semiconductor materials has the potential to revolutionize the world of electronics. Faster chips with reduced heat dissipation will pave the way for more advanced and efficient electronic devices. While there are still technical challenges to overcome, the progress made by researchers is promising. The integration of SEG technology with silicon carbide opens up new possibilities for high-voltage applications such as power electronics. As technology continues to evolve, it is exciting to see the advancements in semiconductor materials. Each discovery brings us closer to a new era in electronics, where faster and more efficient devices become a reality. What are your thoughts on this breakthrough in semiconductor technology? Share your opinions in the comments.